Welcome to the 110th Theoretical Physics Colloquium by Professor Berndt Mueller, who's James Duke Distinguished Professor at Duke University. He received his PhD from Goethe University in Frankfurt am Main. After that, he was a research assistant at Goethe University and a research associate at the University of Washington. After that, he received a professor position at the Institute for Theoretical Physics at Goethe University and was there until 1989. Since 1990, he is a professor at Duke University. Since 1996, he is a Duke professor at Duke University. Between 1999 and 2004, he served as the Dean of Natural Sciences at Trinity College of Arts and Sciences at Duke University. And between 2013 and 2020, he served as the Associate Director, Laboratory Director at Brookhaven National Lab, NPP, Nuclear and Particle Physics Directorate. He received a number of prestigious awards over the years. He is a fellow of the American Physical Society, American Association for Advancement of Science. He received a Senior U.S. Scientist Award from Hewlett Foundation, Jessa Beams Award in 2007, and finally in 2021, Hermann Feshbach Prize from the Division of Nuclear Physics of the American Physical Society. He's an expert in theoretical nuclear physics, particle physics, works on extreme energy density, nuclear matter, quantum chromodynamics, nuclear forces, quark-gluon plasma, heavy ion collisions, and many, many other things that I wouldn't be able to list all. He's a co-author or author of something like 7 or 8 textbooks and monographs. And today he will be talking about thermalization, hydronization, and entanglement. And with that, I'll give the microphone to Berndt.
So thank you. Thanks for the invitation to give the first ASU colloquium of the year. That's an honor and a pleasure at the same time.
It's our honor, really.
What I'll try to do today is to give you a few ideas. I won't actually present final results on anything, but maybe what you will find is that there are some interesting problems on which you yourself might be interesting to work. So overall, the topics involve thermalization, hadronization, and entanglement, and you will see how they are connected, especially in the last part of the talk. Much of what I talked today is contained in a preprint that Andreas Schäfer and I put on the web about 2 months ago. Here's the archive number if you're interested. And at the end, I will mention the project that a very talented graduate student from Yale, Joseph Dominguez Lab, has started to work on with us. So let me begin with a picture that you all know, relativistic heavy ion collision. And I distinguish here 5 stages. The one is the initial stage, that is the nuclei before the collision. Then we have a period of pre-equilibrium where thermalization happens. Then we have a relativistic fluid that we all know, the quark-gluon plasma. And then eventually the system hadronizes, and the hadrons are colliding with each other and eventually freezing out and being detected in the detectors. Now, when you look at this, you find that we have good and demonstrably rather rigorous formulations of 3 of those phases. When I go back here, you see the 3 that are not in picture frames, namely the initial state, where we have a color glass condensate description, the relativistic fluid stage, where we have viscous hydrodynamics, relativistic hydrodynamics, and finally the final hadronic stage, where we have sophisticated hadronic transport models. But we have much less reliable descriptions for the 2 stages that are in the picture frames, namely the pre-equilibrium and thermalization and hadronization of the quark-gluon plasma. And the reason for this is that they are, from a quantum field theory standpoint, rather messy. We have models for them, models that seem to work quite well, but we don't really have a fundamental, good understanding of them on the basis of quantum field theory. Now, However, we have other powerful tools that can help us describe these stages. And one is holography, that's based on the ADS-CFT duality that has been particularly applied to the thermalization stage. And of course, we have only really models for the hadronization stage, where we assume that equilibrium persists and simply the conserved quantum numbers are matched on both sides of the transition. Let me also remind you that heavy ion collisions are characterized by 3 distinct scales. This is, of course, very rough. There are many more detailed scales that emerge in the description, but the main different ones that are independent of each other in principle, can be independently controlled, is the scale of energy deposition. In the color glass condensate model, it's the gluon saturation scale, or in a more statistical model, it would be the initial temperature at thermalization, which are the two are connected. And these can be controlled experimentally by changing the collision energy. The intrinsic QCD scale is not controllable. That's simply there. It is the scale of the running of alpha S, but also it is, of course, dictating what the pseudocritical temperature is that we now know from that is to be around 155 MeV. And finally, we have the scale of the nuclear radius, which controls the size of the fireball. And for a heavy nucleus, that's in the range of about 5 to 10 Fermi. And what you can see here is that these scales are clearly separate. The higher the energy, the larger the saturation scale. It's in the lower GeV range. So we have scale differences of a factor of 5 or 10, which is good from a theoretical point of view, because that allows us to develop effective theories that describe the different physics between these scales. And as long as these 3 scales are very different, there are theoretically well-justified descriptions that are possible. Of course, when 2 of these scales become comparable, the physics may be very interesting, but it is difficult to control. In the case of the saturation scale, that obviously is when you lower the collision energy, you get into a range where the initial temperature is not much different from the pseudocritical temperature. When you look at smaller and smaller systems, then the nuclear radius is not that different from an intrinsic QCD scale. So this is something where I'd like to stay out of today, because I want to deal anyway with the parts of the evolution that are inherently difficult. Clearly, the physics near lambda QCD requires a non-perturbative approach. And what we've mainly made use of here is lattice QCD, which works in equilibrium. It has very limited ability to allow us to explore in a quantitative way and a reliable way non-perturbative physics, or the ADS-CFT duality holography, and I'll talk more about this today. So let me begin with thermalization. We have a conundrum from the experiments that's well known. The extreme applicability and agreement between data and model of the thermal model for particle emission. And this has carried from SPS energies up to the highest LHC energies, where just 2 parameters, namely the temperature and the baryon chemical potential, have allowed to describe a vast array of data. And this is quite astonishing that a system would thermalize to the extent that you can simply describe particle yields at the end in terms of thermal quantities. And it is telling us something about the physics of the system. The most astonishing fact here that I know is the famous hypertriton, which is a very, very weakly bound state, binding energy of less than an MeV and a radius that is almost as large as the nuclear fireball. And there is a fundamental question of how this particle can be emitted with a thermal yield from a fireball that has a temperature that is hundreds of times larger than the binding energy. Now, I know that there are coalescence models that try to explain this, but this, I think, is still remarkable. And one asks the question whether there is maybe a more fundamental underlying principle here that can explain this remarkable effectiveness of the thermal model. This leads us to the question of how thermalization is expressed in quantum mechanics. And of course, we have the experience in physics that interacting systems thermalize and attain a state of maximal entropy, some faster, some slower, but that's the general principle. On the other hand, in quantum mechanics, we know that an isolated system, and a nuclear collision is one of the best isolated systems we have in nature, because it happens in the vacuum with ground state nuclei colliding, that such a system evolves unitarily. And if you naively calculate the entropy, the von Neumann entropy of such a system, then if it's in a pure state in the beginning, it will always remain in the pure state, no matter how complicated it is. So the von Neumann entropy always remains zero or as low as it is in the initial state. The resolution of this contradiction or apparent contradiction is entanglement. It's entanglement because different parts of the system, if it's an isolated system, or if it's a system in contact with a heat bath, the system and the heat bath become quantum mechanically entangled. In other words, their quantum states become entangled with each other. And if you look at the entropy of only a subsystem or only the system and not the heat bath, and you define the entropy as the usual von Neumann entropy of the subsystem only, then you find a value that grows with time and eventually approaches equilibrium. And this entropy of a subsystem in a quantum mechanical system is called the entanglement entropy. It measures how much the wave function or the state of the system is intrinsically phase correlated with the wave function of the rest or with the heat bath. A very nice example where you can show this really easily analytically is the so-called thermal field double. It's a state that you can generate if you have two copies of a quantum mechanical system, two identical copies, which I call A and B. And you could construct a pure state. This is this wave function capital psi here as a sum over e to the minus e over 2t, a factor in front of product states of psi and psi A and psi B. So this is a coherent superposition of states of the double system with a coefficient in front of each of these energy eigenstates. And if you now take a trace where you trace over, say, system B, then what you find is that you get an expression that is exactly the thermal density matrix of system A. So in other words, by this construction, you can construct a state that is a pure quantum mechanical state of a larger system, but is exactly a thermal state of the subsystem. And there's very nice work that's been going on over the last several years in how to make use of this and how to generalize this concept. But of course, this does not include any dynamics here. It's just an ad hoc construction. The question is how that arises in nature on the basis of internal dynamics of quantum systems. And here there is a principle that has appeared that seems to be quite general, and that's called the Eigenstate Thermalization hypothesis. What it says is that if you look at a complex quantum system, and measure its properties using observables, reasonable observables, not artificially, strangely constructed observables, described by physically meaningful operators, then these are sensitive only to parts of the complex quantum system. So instead of dividing the system into two separate parts, what you do is you look at the system from the point of view of its intrinsic properties, and you divide them in those to which a certain operator is sensitive and all those properties to which that operator is not sensitive. And then it suggests that when you look at the system with such an operator, then you find in the stationary state, and the reason one uses energy eigenstates here is because they're stationary. So in other words, they describe the long-term behavior of the system. And then the postulate is that an isolated quantum system may exhibit these thermal properties in the sense that you can describe the expectation values and the matrix elements between different energy eigenstates of the system of an operator A in terms of a very simple expression. And that expression is given here. It has a diagonal part that is simply the expectation value of the operator. And then it has a second off-diagonal part, which is given by a random matrix that's normalized. It could be a unitary or orthogonal ensemble, and a factor that takes into account the entropy, the microcanonical entropy of the system as a function of E. So that's a statistical factor. And then a function f of E and omega, where omega is the difference between the energies, which is, so to say, the function that describes the dynamics of the system around the equilibrium. Well, it's a spectral function. For a given E, as a function of omega, it can be viewed as a spectral function. These off-diagonal matrix elements are strongly suppressed in a large system because the microcanonical entropy is large, and so this factor is very small. These terms here describe the thermal average of the ensemble, as I already said. Using this ansatz, you can derive many properties of statistical systems in thermal equilibrium, although you have described them in terms of quantum mechanical eigenstates. And so, for example, you can determine what is the average, long-time average of an operator A, and you find that it is given by an expression that you would get simply by using a Gibbs ensemble. You can look at the quantum fluctuations. You find that they are equivalent to the thermal fluctuations of the system in statistical equilibrium. And you can look at the autocorrelation function averaged over a long time, and you find that is related to that spectral function. So in this way, what you find is that quantum mechanical time averages can be mapped onto statistical averages that you get in standard statistical quantum field theory. The question arises, of course, which systems exhibit such behavior, right? Because you've written down an expression, and for a given system, in principle, you don't know whether it actually has that property that over long periods of time, and in particular the energy eigenstates have these properties. There is a common consensus that systems that are called chaotic quantum systems satisfy this energy eigenstate hypothesis. And the definition of chaotic quantum system here is one in which, if you look at so-called out-of-time correlators, that is correlators between non-commuting operators, in this case, I just took generally the position and the momentum, but it could be something else. You take the commutator at different times, 0 and t, and you measure this correlation function. It grows exponentially with time. It turns out this is not true for very long times. It reaches a saturation, but for short times or intermediate times, this kind of behavior is found. This lambda here is called the quantum Lyapunov exponent. It's the analog of the Lyapunov exponent in classical chaos theory, but it is defined here in terms of these correlation functions involving out-of-time correlators. Now, this is difficult to prove for a given system because one has to actually solve the full time evolution of the system in order to show that it has this. But in principle, if you have a system and if you are able to follow the quantum mechanical evolution, you can do this calculation and find what the quantum Lyapunov exponent is. And people over the last decade or so have done that extensively for systems that are small enough to be put on a computer. The other question is, how big a range in this frequency omega, the difference in the two energies, is allowed in order for the formula that I gave you that ETH formula, whether that is actually valid. And so this is equivalent to the question of what time scale that thermal behavior becomes established. And it turns out that, and this has been recent insight in these model simulations that I just briefly mentioned, the answer depends on which observable you look at. It's not universal. So in other words, it is not just universal for the system, but it also depends on the operator you look at. There is a generic time scale, and the generic time scale in such system is called the Thouless energy, which can be related to macroscopic quantities, namely the diffusion coefficient D and the macroscopic size of the system. But for some observables, it turns out that that time scale is much larger. And is much larger parametrically with the size of the system, which can be up to the L to the D in addition, if you have a system with dimension D. So this is recent work, and it's been demonstrated that that is possible. So this is a non-trivial question to answer. Not quite a surprise, because when and how thermal behavior emerges, of course, is something that is inherently difficult, but this is under investigation for systems that are currently can be handled. Now, it will be interesting for heavy ion collisions and to get an estimate of that Thouless energy. Well, we know on average in QCD what the diffusion constant is. It's related typically to 2 pi or so times the temperature inverse. And so if you write down the formula, what this is, parametrically is given by this expression here, pi t, the radius of the fireball squared. And for a big fireball, you find that this is of the order of 100 Fermi over C inverse. This is a very long time. So what we cannot expect in a heavy ion collision on the basis of these arguments is to reach full thermal equilibrium. On the other hand, we're not looking at all operators. We're looking at certain operators. And in particular, we're looking at operators in the end that measure hadrons. And so the question is whether for operators of the type that involves hadrons, which are more localized operators than the whole fireball, or correlations among hadrons, which can involve larger distances, of course, in Hanbury-Brown twist measurements, whether this applies. So this is an interesting question to which we don't have an answer at this point.
Berndt?
Yes.
A quick question. It seems like you're talking about the global equilibrium versus local equilibrium. Is that the spirit of the last question you were trying to say?
Right. So yes. So in a sense, you can phrase that in the way in exactly that way, local versus global equilibrium. But of course, when we look at Hanbury-Brown twists, we're looking for the source size. So we're actually looking at emissions from different parts of the source, and we make the assumption that those are given by thermal emission probabilities, right? So in other words, whereas I could see for say, the emission of a pion, a size of only 1 Fermi being relevant, when I look at 2 pion correlations over a distance of the size of the fireball, that's no longer true. And if I look at the emission of a large particle, like a resonance state or the hypertriton, that's certainly not true, right? So these are so these are the questions. But as I said, we don't have an answer to it.
Okay.
There's much more that we don't know, actually, than what we know. As I mentioned, the behavior that underlies this formulation of thermal behavior of isolated quantum system, it can be demonstrated for small finite systems. So typically, these are called tensor networks or equivalent, where you can do classical numerical simulation of the Schrödinger equation, or you can classically diagonalize the Hamiltonian, and typically this requires less than 20 degrees of freedom, usually of the order of a dozen. certainly nowhere near what you have in a quantum field theory. There are certain larger systems, matrix models, such as the so-called SYK model, where this has been demonstrated. And it turns out there are also models of 1+1 dimensional gravity and conformal field theories, which have particular analytic properties where we can also show that. But none of these are real systems that occur in nature that we're dealing with. In such systems, one can derive really exact expression for the spectral density and its correlations. And one can determine the long-time behavior, and it generally agrees with what people expect on the basis of general expectations. But again, does this work in practical reality? It turns out that if you have gravity theories that have a holographic dual, then you can show the differences, or can calculate the differences, certainly in an asymptotic way, between the correlation function and the product of the eigenvalues, of the expectation values of the energy densities of the spectral densities. And they're related to so-called complex saddle points in the action that relates to higher genus topologies. These are so-called Euclidean wormholes. I've given one reference here. There's a lot of work that's been going on. And what this raises actually is intriguing questions about what the relationship between the quantum field theories on the edge that we're trying to describe holographically and the holographic duals is. There is now a consensus that actually the holographic dual does not necessarily describe a single quantum field theory, but a family of quantum field theories. But this is under debate. And I've given here a reference for this as well.
We have a question.
Mm-hmm.
Ulrich, go ahead.
Yeah, Berndt, for the models that have been shown to show ETH behavior, do they share a feature that you can isolate that is responsible for that one could use for guiding ourselves for other theories that might have this behavior?
Yeah, they all show that quantum chaotic behavior, namely that the out-of-time correlators are growing at small and intermediate times in exponential fashion.
Okay, thank you.
Right. So if one believes that one maps onto the other, then one has a criterion for that. But that's, of course, not mathematically proven. So now let me turn to entanglement. I already mentioned quantum entanglement when we talk about the thermalization of isolated systems. Here, more generally, if you have a bipartite system, that is a system that consists of two parts, they're entangled if the density matrix of the combined system is not equal to the product of the density matrix of the individual systems. And one defines a entanglement entropy, as I already expressed in terms of the von Neumann entropy of the subsystem. And it doesn't matter actually which subsystem you look at, the entanglement entropy can be calculated from either one and they're identical. In the thermal sense, in the traditional sense, what you really have is the entanglement between the system and the heat bath. And we talked about this. There is a concept of maximal entanglement between two particles. It's two particles in such a state are called a Bell pair, and that is when they're entangled in the form that I wrote down here, namely as either a spin 0 or spin 1 state, where the overall spin is quantum mechanically constructed from the spin of the individual particles. But of course, you can generalize that to other quantum numbers. There is a very important property of entanglement, and that is if you have more than two particles, then a single particle cannot be maximally entangled with more than a single other particle. So in other words, if you have maximal entanglement in the sense that I just said, then it has to be between one pair of particles. If you have many particles, then they all can be entangled with each other, but the degree of entanglement of one particle with any particular other one has to be much less than 1. And there is a function that's been defined. I don't want to go into detail. It's called the tangle function that can be used for such calculations. And then when you sum up the entanglement among all the particles, you find that altogether one particle entanglement with everything else has to be less than 1. And so this means then that the fraction of entanglement shared between 2 particles out of that ensemble of particles has actually to be of order 1 over n, or at least on average. So in heavy ion collisions, let's think about that in this form. The 2 nuclei collide. They're initially in a pure state. They move at approximately constant speed in the accelerator. So they are in a reasonably well-defined energy eigenstate. And so we have a system that actually is prepared in very good approximation in an energy eigenstate. The internal parton wave function of each nucleons are also approximately pure states. An isolated nucleon, of course, that is true. In a nucleus, they can exchange quantum numbers as they collide, but the result and the experience from nuclear physics is that a nucleus, to very good approximation, consists of individual nucleons that are color singlets and have a definite spin and a definite baryon number. So again, we have here rather well-defined initial states that are not entangled with each other. And certainly the partons in the 2 different nuclei are unentangled with each other. So all entanglement among the partons has to be built up by interactions during the collision. In the longitudinal direction, that's very easy because all the nucleons in the same transverse direction that overlap during the collision, of course, interact with each other. They interact in a very short period of time. And so their partons become entangled by these interactions. But that's not true in the transverse direction. There, the entanglement has to be built up by causal spread of entanglement, by interactions. And so the question is, what actually is the speed at which the entanglement in the transverse direction happens in QCD? In general, the way that the entanglement can propagate in a system is called the butterfly velocity, because it describes how quickly, in principle, quantum mechanical causal relationships can be spread throughout the system. In the case of QCD, we don't know what the butterfly velocity is. We don't have any way currently to really calculate it, but it's been calculated in holographic systems. So, for example, in the famous N=4 supersymmetric gauge theory, one knows that it depends on the dimension. And in 1+1 dimensions, it's the speed of light. In 3+1 dimensions, it's about 62% of the speed of light. And when you look at these numbers, it turns out they're very close to the speed of sound. But there's a general consensus also that entanglement cannot be transmitted by sound waves because they're classical waves. And so why this coincidence happens, I think at the moment is unknown. And it would really be interesting in principle to find out how this entanglement spread happens in real QCD. But as I said, we don't know that. The other emphasis that I wanted to give here is, before we go on to the next section, is the entropy. We often talk about entropy in heavy ion collisions, and they're usually derived from experimental data. And what we usually really mean is the entanglement, the entropy that we calculate from single particle distributions. Sometimes one includes 2 particle distributions, but they're certainly not measuring the really microscopic entropy of the final state. When I look at the system and divide it into rapidity windows, and I ask what is the entanglement entropy of that subsystem in that rapidity window, then of course it's given by the standard expression. And if I make that window larger, then I will generally find that the entanglement entropy increases until the system reaches a size where it begins to become comparable to the whole size of the fireball. That is, when it extends over the full beam rapidity range, delta capital Y. So in other words, for small values of the rapidity window, the entanglement entropy should grow with the size of the window. But when eventually it goes to the rapidity window size, where I see the full system, then I should recover that it is in a pure quantum state. And so the entanglement entropy should go to 0. So in other words, if I plot this schematically for small rapidity windows, my entanglement entropy of that part of the system should grow linearly. Eventually, it should reach a maximum and then fall back down to 0. Of course, it won't be a triangle. It will be a more complicated curve, but that's the general shape. Such a curve for any isolated system was postulated in the 1990s by Don Page. It's usually called the Page curve, and we'll come back to that in the context of hadronization. As I mentioned in the beginning, the final state entropy usually is inferred from single particle spectrum and the distribution of particles. So one has a concept of the single particle entropy. And because this does not take into account the quantum correlations between particles, that means that it can continue to grow. So in other words, it does not show the property of the Page curve. If I look at the whole fireball, I add up all the contributions from all the different rapidity windows, and eventually I reach the overall entropy, single particle entropy of the fireball. So the picture is a little bit like this. The real entanglement entropy as a function of rapidity has to be a curve of this form, whereas what I usually calculate using particle distributions continues to grow. And that discrepancy really is what's encoded in the quantum mechanical entanglement. There's very nice work by the North Carolina State Group from about 2 years ago, where they actually look at this in the context of gluon distributions, and they've called this the entropy of ignorance. So whereas this is the real quantum mechanical entanglement entropy, this would be the entropy of ignorance that, of course, grows if I look at the larger part of the system, but don't measure all its intrinsic properties in microscopic detail. So I'll very briefly go through holography because you're all familiar with this. The principle, it dates back originally to, the concept of Bekenstein that the horizon of a black hole has an entropy and that it is the maximal entropy that any volume of space of that size could contain. And so this means that for the case of the black hole, the entropy is not proportional to volume, but is proportional to an area that is a lower dimension. And this suggests that somehow all the degrees of freedom at the Planck scale, at the quantum gravity scale of a 3-dimensional space can be encoded in a 2-dimensional hologram. And that idea was also proposed in the 90s by almost at the same time by Toft and by Susskind. What was missing for a long time was a real model, but that was provided by the discovery by Mandasena of the ADS-CFT duality, which is by now the most cited paper in physics of all times. So what he proposed was that there is a strongly coupled cousin of QCD, so to say, the SUN gauge theory with n=4 supersymmetries and many colors that's dual to a weakly coupled string theory in 10-dimensional space with a particular topology, which is 5-dimensional anti de Sitter space and 5-dimensional spherical space. And because the dual is weakly coupled, it is solvable, whereas the strongly coupled gauge theory is, we don't have any rigorous methods to solve. So this is really a powerful method of mapping a system that we would like to understand, but cannot, into a system that we actually can do calculations in. What is even nicer is that in the limit of very large numbers, effectively the string theory becomes classical gravity. And so we have standard analytical and numerical techniques that allow us to do rigorous calculations. They're complicated numerically, but they are definitely within the range of what is possible. The quantum field theory, in this case, lives on the edge or the boundary of the anti-de Sitter space at infinity. And so the duality means that you can take an observable in gauge theory and map it onto an object in the string theory that you can then study. What is interesting from the point of view of thermalization is that if the anti-de Sitter space contains a black hole, then the boundary gauge theory is thermally excited. And so you can think of thermalization in the gauge theory as the formation of a black hole in the gravity theory, the dual gravity theory, where the temperature is connected with the horizon radius. All very nice and has been used in multiple ways. The first use really was thermalization, where you can think of heavy ion collision as which proceeds in the quantum field theory edge as being mapped into a dual holographic picture, where when we think of QCD, we pull strings of flux tubes between the nuclei, and then in the holographic description, these begin, because they're energetic and therefore feel the gravity, they sink into the bulk, and eventually, if there is enough of that, they will form they will form a black hole, and with a horizon that allows you to describe the thermal physics that emerges on the in the quantum field theory edge. So this can be treated in multiple ways. Well, initially, people were doing this in a schematic way, where they created, injected just some energy, and they looked at how this evolves and how it eventually forms a black hole. The question that arises here is, how do you calculate the entropy? And one of the important aspects of the gravity description is that there is an effective way of calculating the entanglement between different parts of space, which is called the HRT, or Rubeni-Ryu-Takayanagi prescription of using the minimal surface that extends from the region on the quantum field theory edge, from the boundary of that into the holographic dimension. And so if you have an event horizon, that it turns out that this surface hugs the event horizon over most of the area. And so what actually it measures is the entropy of that. The area of that surface becomes equal to the entropy of that region in the quantum field theory space, that except for proportionality constants. So what this makes, what it makes possible is that the calculation of entanglement entropy between two different regions of space in the quantum field theory, which is in principle a very difficult calculation. In the general case, it is a so-called NP-complete problem, can be mapped onto a problem that is really calculable, namely the calculation of a minimal surface in a geometry, in a higher dimension geometry. But that's a technique, that's a problem that we have techniques for, and can perform the calculations. So in this way, you can actually look at the way that thermalization happens. I don't want to go into detail here because that is all old stuff, and you can look at the papers. This has been generalized to much more complicated situations that are much more akin to heavy ion collisions, shockwave collisions. Here is a collision where you see shockwaves colliding in time, and then they inject energy effectively in the region between the two, and you can study all the properties of that system and how it thermalizes. And you can really show very nicely how the entropy grows using the growth of the horizon area of the black hole in the holographic fifth dimension. So this has had a lot of successes, but that's not the purpose I want to talk about today. So rather what I'd like to do is come back to hadronization. This was the area that we really don't have a good quantum mechanical formulation of. And so I want to talk about that a little bit as the last part of my talk. This slide here shows a hadronization surface that's been calculated using viscous hydrodynamics. Jean-François Paquet produced that slide, and it shows the central region, the proper time in a heavy ion collision, gold at Rick, intermediate centrality. Tau is the proper time, and here we have the transverse direction. And what you see is that initially we have here in the inner region, we have the quark-gluon plasma, which then expands and eventually cools. And it reaches the pseudocritical temperature in really two parts of the surface. One is a time-like surface over most of the evolution, which stays almost at the same distance. So this is almost cylindrical. And then we have a space-like surface where the whole interior of the fireball has reached the critical temperature and then eventually hadronizes. So this is hadron emission from a expanding fireball. This here really is the bulk conversion of the fireball from quark-gluon plasma into hadrons. So that's what we would like to also understand, how we can describe this in a quantum mechanical way. Here's another picture that comes from Uli and his graduate student, Christopher Plumberg, where they very nicely use two-particle correlations, the origin of pion pairs of different set of mass momentum to isolate the different regions of the emission surface. And so if they look for small pairs that move slowly, they find that it's all dominated by the space-like part of the bulk transition, whereas if they look at energetic pairs, then they find that they are dominated by that emission from the time-like part of the surface. So they're really, in a sense, not absolutely, but approximately distinguishable two mechanisms. When you look quantitatively, and I made the estimate that this is approximately 80% of the pions, and this is about 20% of the pions, but I don't think we have a rigorous calculation for that. That's an estimate. So let's now think about the hadronization and how the quantum mechanical information is transmitted in that process. So initially, we have only the quark-gluon plasma. It's a pure state arising from the collision of the two nuclei, but it's a pure state with apparent thermal properties. When it begins to emit hadrons, they are emitted from the surface initially and later from the bulk. And these particles are emitted separately, and they are entangled quantum mechanically with the interior, the remaining fireball, right? Because they contain information that is previously contained in here. And since all that information is combining to a pure state, then this still will be pure state. So the information has to be shared between these two different parts of the fireball. As you grow and emit more and more hadrons, then what I described as the page curve comes into play, because now the information that can be the entanglement entropy of the hadrons alone has to equal that of the plasma alone. because of that balance. And therefore, the smaller part of the system is really what determines what the entanglement entropy is. So by that time, the entanglement entropy has already shrunken. In other words, the hadrons are no longer a mainly statistical state, but they actually contain quantum mechanical entanglement information between them. And eventually, when the quark-gluon plasma is gone, then all the hadrons have to be in a highly entangled pure quantum state that looks thermal to practically feasible experiments. But the entanglement has to be encoded somehow in the hadrons and in that process. It turns out that that process has been looked at in great detail over the last decade in the case of black hole information, black hole evaporation. In a sense, this is similar, because in the case of black holes, what you find is that what you have is that Hawking radiation is emitted by the black hole. Here is the event horizon. This is the remnant of and the singularity inside the black hole. And each pair of each Hawking particle that is emitted actually is associated with a paired particle that goes into the black hole. So these are in a good quantum state here, these two blue ones, the two green ones, the two red ones. And that means that in this case, the information that is carried in the Hawking radiation that's emitted is paired in an entangled way with information that resides in the black hole. So in other words, as you build up entanglement entropy in the radiation zone, you also build up the equivalent amount of entropy inside the black hole. And so the radiation and the black hole become entangled. And because this is a process in which the particles actually don't collide with each other, but in which they actually propagate in a background metric, it turns out that at least in simple models or in reduced dimensional models, this is the process that can be traced. And one can find that there is, one finds that there is a surface, which is here, that contains all the information inside the black hole. This surface, in the interior of that surface in the black hole, contains all the information that is in the Hawking radiation. And so overall, it remains a pure quantum state. But if you look only at the Hawking radiation, then you think you have a thermal ensemble. This state here can be actually calculated because of the properties that I mentioned, namely of basically ballistic motion of the particles inside the black hole, and it's been called the island. So this island grows in the same measure as the amount of emitted Hawking radiation grows. And eventually, when the black hole has shrunk below approximately half its mass, then it turns out that that information becomes, and again, is released back into the Hawking radiation. And so ultimately, the Hawking radiation obtains a pure quantum state. The way that this can be traced is really by the fact that you have a geometric description in which you have this surface that allows you to quantitatively measure what the entropy, the entanglement entropy is. And this is here the curve that I showed, in the sense I showed before. This would be, if you only look at the Hawking radiation alone, then you will find that its entropy grows and grows and grows. But the real entropy in it has to decline again once the black hole shrinks below half its mass, roughly. So in other words, this should be this curve has now been calculated in 1+1 dimensional models. There is a clear description of how that works. And the idea would be can we apply this to heavy ion collisions? There's one more context, one more concept that I want to mention in this context, and that is, how is that connection in the gravity theory between the emitted radiation and the information in the interior of the black hole made? And the idea here is that you have actually a geometric connection. If you think of the Hawking radiation particles as miniature microscopic black holes, then you can think of them as being connected geometrically with the interior of the black hole through what's called an Einstein Rosenbridge. So this is here in a macroscopic case where we have two regions of the universe. They can be connected through the regular space, but they can also be locally connected by a geometric bridge. There's been lots of speculations about that. Could you travel through them and so forth? In most cases, that's impossible. But the point is that from a theoretical description that allows you to describe geometric connections between regions of space that are far apart in a causal way. And so the concept that in a quantum theory, the entanglement can be described in terms of such Einstein Rosenbridges, if you are dealing with gravity, was proposed by Maldacena and Susskind. And there's been a lot of work in that direction quantitatively to verify this. Now, in order to apply that to QCD, of course, you need a gravity description of QCD, and this is where the ADS-CT duality comes in. If we think of the evaporation of the quark-gluon plasma, then, well, in the recombination model, for example, you have a meson or baryon emerging because you have quarks and antiquarks, or three quarks combining at the surface and being emitted by a hadron. So what this means is that the emission of a hadron leaves a particle-hole pair leaves holes in the quark-gluon plasma, either quark hole or an anti-quark hole. And so there is a quantum correlation between the meson and these hole excitations in the quark-gluon plasma. Of course, these holes are not good quasi-particles. We know in general, there are no good quasi-particles, certainly not near the critical temperature where the emission happens. And so this becomes a very complicated process of how this state that is quantum mechanically entangled with the emitted hadron propagates in the quark-gluon plasma. We can't use quantum field theory to trace that, but in a holographic dual where we can calculate the entanglement entropy using a minimal surface in holography, that could become possible. And in that way, one could hope to actually formulate it into a page-like curve where one can show that the entanglement entropy of the emitted hadrons that initially grows eventually shrinks back to zero and they get back to a pure state. So the holographic picture of such a process would somewhat look like this. Here, this is the picture in real space that I described. In a holographic space where you would start out with a quark-gluon plasma that has a black hole horizon that as a function of time evolves. The emission happens on those edges of that surface where you reach the critical temperature. That's either in the radial direction at the surface of the fireball, or it is in the temporal direction when the whole fireball reaches the critical temperature. And so the process of the entanglement here on the surface looks like this, which would be the analog of this picture here, but you could trace it in the dual down here using an entanglement surface. So let me briefly come back to this here. Let me say a few words about that bulk transition here. There is actually in the holographic description, there is an analog of that transition. It's called the Hawking page transition. And if the black hole temperature shrinks, you find that there is a certain temperature at which the black hole becomes unstable against fragmentation. That's been known for a long time. It's the Hawking-Page transition. But what hasn't been done so far is really develop a non-equilibrium picture of that. And so normally for the large black holes that in the holographic description we use, we have a effective potential where the minimum corresponds to the black hole radius that exactly corresponds to the temperature of the environment. But and that's the minimum, and so this is stable. But when the temperature is lowered, then eventually you reach a point where that minimum is equivalent to the minimum in which there is no black hole, or in other words, the black hole radius is 0. And so beyond that, the black hole becomes unstable, and it becomes manifestly unstable at a minimum temperature that's a little bit less than that. This process of is a process that hasn't really been investigated in detail. But in principle, if one could look at this, it would be possible to develop a transition not only for the evaporation of individual particles, but also for the bulk transition. In the pure ADS CFT, the simple model, this is a first-order phase transition, which is, of course, not what we have in QCD, but one can model it and fine-tune it using a dilaton potential that's been done many times in the past, modeling QCD and developing either a second-order or even no smooth crossover. So the dual picture would then somewhat look like this. And I make now a cut in the transverse direction here through and snapshots at different times. So initially we have quark-gluon plasma up to the boundary of the fireball with a higher temperature in the interior and a temperature, just the critical temperature at the surface. When you emit a hadron, what you build is a connection between the hadron and the quark-gluon plasma in the holographic direction, where this sinks deeper and deeper into the z direction. And this constitutes then this Einstein Rosenbridge in the dual description that connects the hadron to the quark-gluon plasma and encodes the entanglement. If you have more and more, then you have more and more of these Einstein Rosenbridges. And eventually, when the whole quark-gluon plasma breaks up, you have a network of these Einstein Rosenbridges that are all connected in the holographic space. But on the edge, it looks like individual hadrons. Nonetheless, this then can describe the quantum mechanical connection and entanglement among the hadrons. Another way of looking at this is shown here, where we keep the two dimensions in the edge where the quantum field theory lives. Initially, the green describes the quark-gluon plasma corresponding to the black hole in the holographic dimension. Then you emit more and more, and all these hadrons are connected to that black hole. And eventually, you have a large number of such hadrons, including those that are generated by the bulk transition. So you get a very complicated network of this. And eventually, when the black hole is gone, when the quark-gluon plasma is gone, you only have this connection of these individual entanglement connections between the hadrons in the holographic space. Now, the hope here would be that instead of describing that very complicated network, one has a smooth transition where whether you have each of the hadrons connected through the black hole in a quantum mechanical entanglement, having it connected in such a way here through individual bridges in what sometimes is called the octopus picture of that final state is equivalent. And that would then allow to make a description that matches the evaporating quark-gluon plasma into the emergent hadron gas in a way that's smooth, in a way that's not apparent in the statistical treatment. So let me summarize. There's some simple questions. A simple question is, does QCD exhibit ETH behavior? And what are the relevant timescales for operators that we care about? That's something that cannot unfortunately be answered by Euclidean lattice gauge theory. We need non-perturbative calculations because it's about the time evolution of highly excited states. So that would be an interesting thing to pursue in the context of efforts to actually put QCD on a quantum computer. It may not be possible to simulate a very large system, but to look at small pieces of non-abelian gauge theory may be possible and within reach over the next few years. It would also be interesting to look at the modeling of the quark-gluon plasma hadron transition using the holographic technique by looking at the time evolution of the Hawking-Page transition. That's again something that in principle is feasible with today's techniques, but it is a difficult problem. We mentioned that entanglement of the hadron should be captured by Einstein Rosenbridges in the ADS space. How to do that in 3 or 4+1 dimensions is not clear at the moment, but one could start with a low-dimensional model. And so this is what Joseph Lapp is currently working on by starting out with an analog model in 1+1 dimension. In this case, well, one can look at the breakup of a system into small pieces, which corresponds then in the holographic space to the evolution of a higher genus topology. Here's an example of such a mapping that leads to 3 different regions with gaps in between them. So this would be a splitting of 2 hadrons away from a central region. And one can then use techniques of conformal field theory to calculate the entanglement entropy in terms of minimal geodesics that connect through different regions and look at how this evolves as a function of time. So for a very simple case for a single splitting, this has been done by Shimaji and Takayanagi and collaborators a few years ago. Our idea is to generalize that to multiple splittings to see how this evolves if you take a system and actually break it up into many small parts, and to understand how the entanglement works here by using the holographic techniques in this simplified version. So let me stop here. It's been a lot of things that I talked about. If you are interested in more details and more discussion of open questions, I refer you to the preprint on the archive that I mentioned. There's actually a 2 missing. It should be 2211. I'm ready for questions.
Thank you so much for a very nice presentation. Now let's go to questions. I see Paul Frampton having raised hand. Please go ahead, ask question. Unmute yourself first.
Yes, could you turn to slide 29, please? Now, I have 2 questions, I suppose. The first is a historic, I mean, very historic, actually. In the this question that you have there, or the relation between the Einstein Rosenbridge and the EPR paradox, in a way, entanglement, I mean, these 2 papers, as you know, were both written in 1935 involving Einstein, one of the 2 greatest intellects ever to work on theoretical physics. So the question is, do you think, this is almost impossible to answer, but do you think it's possible that Einstein had any suspicion of what Maldacena and Susskind pointed out 78 years later? That these two papers are intimately related?
It's a curious coincidence. I'm not sure to make more of it, except for the fact that these are two fundamental questions that we're still trying to fully understand today, right? I mean, the way that the wave function collapses when you do a measurement on an entangled state at two very separate places this is what puzzled Einstein, of course, right? It was not the fact that you have entanglement, but the fact that you have this instantaneous collapse of the wave function is what bothered him. And we don't really, I don't think we really don't understand that today. The concept of the multi-connectivity of space-time is intriguing. The fact that you have this connection through holography is also intriguing. Of course, Einstein didn't have that, and so I think, in a sense, the holographic concept has made a connection between these two different ideas possible, which was not really true in Einstein's day. But I think Einstein would be intrigued about it.
Okay, can I ask my second and last question?
Go ahead, please.
Yeah, I agree. So relating to that, of course, the EPR paradox paper, I should say, took the perspective that entanglement is ridiculous and therefore quantum mechanics must be wrong. And of course, now we know that quantum mechanics is correct and entanglement is also correct. So it could be easy to say that the EPR paper is wrong, but in coming to 2022, one of the co-winners of the Nobel Prize is Alan Aspect, who proved that the Bell equalities are in fact violated in 1983, I think. But he makes a big point in his lecture that actually the EPR paper is absolutely crucial for everything, because Bell probably couldn't have written his paper in 1964 without the EPR paper. And he went further and said that the EPR paper is the basis of all of quantum information theory. So in a way, it all stems from Einstein's intellect, although he had, in some vague, in a journalistic sense, Einstein was wrong.
Well, but, Paul, may I contradict here? I don't think Einstein was bothered about entanglement. He knew that entanglement had to be there. What he was bothered about was the collapse of the wave function. And I don't think we understand that today very well. We have learned a lot about how entanglement works. We know that this, combined with the Copenhagen concept of the collapse of the wave function in a measurement, describes nature. But how that collapse happens, what's underlying it, I don't think we really understand. We take it as a given fact. That's what Einstein was bothered about, not about entanglement.
Well, can I very, very respectfully disagree with you?
Sure. I read the paper recently.
Well, I have it under my pillow. You mean EPR?
Yes.
No, I think what Einstein really was bothered by is the fact that the wave functions of the two particles running away from each other had to involve they could not be separated into one particle and the other particle. And so that it seemed to him, I think, I mean, I'm not Einstein, but I think what bothered him was that seemed very non-local, that eventually they could be a billion miles apart, which seemed, I think, perhaps to Einstein to be ridiculous. But of course, I don't know if we're agreeing or disagreeing. But I do think he was not only worried about the collapse of the wave function, I think he was worried, I think he thought that entanglement was obviously ridiculous, and therefore quantum mechanics must be wrong. And not a complete, actually what he said in his paper, I think in the title of EPR, but you've read it more recently than I have, is something like quantum mechanics cannot be a complete description. Is that the title, or I don't have?
No, I think that's correct. Well, I think the jury on that is out as long as physicists explore quantum physics. But I think, Paul, thanks for the questions. Maybe somebody else has a question too.
I'll put my hand down if I can.
Okay. Thank you so much. That was indeed interesting, but let's move on to the next question. Rajiv, please go ahead.
Hi, thank you for the talk. I have a very naive question. So is this butterfly velocity somehow related to butterfly effect in the chaos theory? No.
Can you repeat this? I didn't get all acoustically. I didn't get everything.
So okay, so I'm asking that is the butterfly velocity is related somehow to butterfly effect in the chaos theory?
Yes, it comes from that, because the butterfly effect is basically based on the concept that a tiny causal perturbation can create a big effect elsewhere, right? And so the entanglement is again, in that sense, a causal connection between two different parts of the system, or different regions of space-time, and so the question of how that propagates is related to the butterfly effect. But it's in other words, if the butterfly effect cannot emerge faster than with the butterfly velocity. That's the fundamental connection.
Mm. Okay. Just a small second question, if I can.
Please go ahead.
Mm-hmm.
Yeah, so the second question is, if I understand correctly, we don't know how the entanglement is spreading in the heavy-ion collisions, like the entanglement between the hadrons and the QGP, and then the entanglement within the hadrons. So that spread is not clear, right?
So as I said, the entanglement in the quark-gluon plasma in the longitudinal direction is created in the initial collision.
Yes.
Because all the nucleons overlap and interact. And so their quantum wave functions become entangled. In the transverse direction, that's not the case. And so it needs to be transmitted by the propagation of information. Right? And the propagation of information in a system typically happens by means of some modes. They could be particles that move from one part of the system to the other, or it could be collective modes, or it could be all kinds of other modes. And so that has to happen in a causal way after the collision over a period of time, right? We don't know exactly what does this, because nobody has done this. I mean, nobody knows how to do this calculation in QCD, right? Because we don't have a non-perturbative real-time evolution theory of QCD. We can study this in a dual model of QCD, where that entanglement can be mapped by the propagation of these surfaces, and that's been done, right? So that has been investigated.
Okay, thank you very much.
Okay, I have a question as well. The question is related to the entropy or the page curve that you were showing, the single particle entropy in the heavy ion collision versus the what you call true entropy that includes all the entanglement and everything in the final state. So yes, this curve. You obviously tell us very simple message here that should be true. On the other hand, from the experiment, we only, roughly speaking, measure that single particle entropy. So the question is, how do we even measure this true entropy in principle?
That's a very good question. There is no simple way of measuring the true entropy. However, what the difference between the dashed blue curve and the red curve suggest is that the statistical state and the quantum state have to differ in essential ways. And the question is, and I don't have an answer to that, although I've thought about it, and I know some others have thought about it too, are there ways of detecting some differences? Typically in a multi-particle system, the correlations are encoded either in multi-particle correlations or in phases. And so the question is, can one construct observables that actually are sensitive to those and which survive sufficiently to be detectable? I think the best chance probably is to use correlations among particles that involve conserved quantum numbers. So, for example, baryons and antibaryons, strange and anti-strange particles, and so forth. And there's a paper, I believe, by Raju and collaborators from about a year or two ago, where they make an argument that you could actually look at strange particle correlations. And now, as I mentioned, with the monogamy of entanglement property, the entanglement between two particles has to go down as the system grows, because a particle cannot be more than once completely entangled, maximally entangled with anything else. And so the larger the system, the more difficult it may be to do that. But here is where a smaller system might actually work. And one might use the A-dependence of such correlations to map that out, right? Going from proton-proton to ultimately gold-on-gold. But that's probably easier to do for small than for larger systems because of that property.
Right, right. I see. The natural consequence of that, of course, will be the smaller the system, the better you could see these individual parts, but then less of thermalization, and essentially you're basically going back to more quantum system. So in a way, it helps, but somehow feels uncomfortable. I don't know why.
Yeah, I mean, one has to recognize that in this case, it's probably possible to test certain aspects, but not the whole picture, right?
Right.
But I mean, that's how you do experiments in physics. You isolate certain aspects and you probe them, and then you rely on them being valid in the bigger context.
Right. Yeah, no, it's very interesting. Thank you. I appreciate that. I don't see any other questions, raise hands. So with that, then I would like to thank you again for a very nice presentation. Thanks everybody who joined us, and we'll stop here.